Kia ora team, I hope you're all doing okay. Hopefully the sound is coming through all good. You can hear everything, see everything. And today our goal is going to be to do a bit of a quickfire cover of all three external topics. Now this isn't going to be an exhaustive review of these topics. Hopefully though, what it should give you is enough of an overview to know which parts you need to be spending more time on. We'll have a little kōrero at the end about some study techniques, but essentially we'll just be kind of breezing through each of these core ideas, which will be you'll be needing to know to be able to sit those three externals. So those three externals are mechanics, which is Achievement Standard 90940, genetics, which is Achievement Standard 90948, and acids and bases, which is Achievement Standard 90944. As we're going through this, if you do happen to join live, you're welcome to post any pātaite in any questions in the chat, and I'll do my best to answer it as we're going through. But if you're watching this at a later stage, that's all good too. You can type in or save any questions you may have and bring them to your teachers or to me when we meet up next week. Okay, let's start by going through mechanics first. So the way I've broken down mechanics here was using Known Brain Too Small's review of the topic, and so we're going to cover it in terms of speed and motion, then we're going to look at force, mass, weight and pressure, and then lastly we're going to talk about energy, because those are the kind of major types of questions you'll be asked. You have some questions on speed and motion, you have some questions on those forces, and then you have some questions on energy. So let's go into speed and motion. First thing you need to know is that distance is measured in meters. I hope you all are able to do that. The second thing that might come up, and I think is just a really nice thing to get your head around for mechanics, is in mechanics, the scientists in that space really like to use shortened down words. They're not wordy people. Physicists, they prefer symbols. So if you can use a single symbol to represent a whole bunch of words, that's a good thing in physics. So the symbol triangle, right, or the Greek letter delta, just means to change in, right? And normally we use that symbol where we want to point out that we're not using something in its absolute sense. So for example, you'll see in that formula down there, change in distance, right, delta D. That's trying to make sure that you remember that it's not just, it's 100 meters, it's the distance has changed. It started at 0 and gone to 100. That helps you to avoid making those mistakes where the person was already at 100 meters away from the origin, and then they moved to 200 meters. The difference there is 100. Right? The change in their distance is what we care about, right? So the second thing is that, now I know a lot of you will know this, but there might be some of you out there who don't, but that slash symbol that we sometimes use means to divide by something. Actually, the divided by symbol is really a slash. Those two dots above and below it, they're placeholders for numbers. If you think about a fraction, right, you might have like half, 1/2, right? It's the dot above the dot. That's what it's there for. So there's a couple of formulas we need to know regarding speed and motion, and these might come a little bit intuitively to you. So velocity, or speed as we like to say, but velocity indicates it has a direction, is our change in distance over our change in time. So if we travelled 10 meters and it took us 2 seconds to do that travelling, then our velocity would be 5 meters per second. Right, 5 meters every second. And we can use the units m divided by s, meters per second, but as we go up in the levels, it becomes harder and harder to just have a big divide symbol in the middle there. So what scientists tend to do is they use this other form of notation where you times the m by the s, and then you time, or you're putting the s to the power of -1, which it turns out mathematically is the same thing as divided by s. You might be like, why are they bothering to do that? Well, that comes up when you get to those more complex symbols. So we're trying to introduce it to you now. Acceleration. Now, acceleration has a little a and we use a little a for acceleration rather than a big A because we use big A for area or surface area. And it's really easy to get those two confused, so just keep it in mind. Acceleration is a little a. Acceleration is related to a change in speed. So if you slow down, you were initially going quite fast, now you're going quite slow. The difference in speed is your delta V, your change in velocity. Now, how quickly you change your speed refers to your acceleration. If you do it really fast, i.e. you don't take much time at all, right, then your acceleration was really quick. If your change in speed was slow, right, took a long time to do it, your acceleration was slow. That's why we divide by our change in time. Our units there, right, it's our speed change per second. So it's meters per second, but already that starts to get a little bit complex. That's why we use ms to the -2, right? So there you go. Those are the basics. You will be expected to be able to understand these as they could be plotted on a graph. The two types of graphs you will get are distance time and velocity time graphs. Both have time on the x-axis, right? We always tend to put time on the x-axis, and then we're measuring are either distance away from the origin or the velocity of the object, right? And remember, x is to the left and y is to the sky. And the key thing to know for our distance time graphs is that the gradient of a distance time graph is the velocity, right? The gradient of our velocity time graph is our acceleration, which is pretty neat actually. So kind of a useful thing there. And so let's have a look at some of these distance time graphs in action. So you can see we've got our distance in meters on the left there, on that y-axis, and we've got our time in seconds on the x-axis. Now here are a few different examples of graphs you might be given. Your job would be to use those distance and time values to be able to calculate those. I'm not going to go through them here. If that's something you don't feel super confident about doing, if you're looking at that and you're like, oh man, I think I would make a mistake, maybe that's something to go over. The key thing here is acceleration in terms of increasing speed is going to look like your slope increasing over time. So that's going to produce this curve. Deceleration is going to produce the opposite direction of curve, where your graph becomes shallower over time. If the graph is horizontal, the organism or the thing is staying in the same place relative to the origin each second. That means they're stood perfectly still, right? They're stopped. And that's going to be different to our velocity time graph, which I'm going to show you here. So make sure we're always looking at that y-axis when you're doing these. Velocity measured in meters per second, and our time measured in seconds. Here you can see that their speed starts off, their velocity starts off at 0 meters per second, and it increases to 3 meters per second. So that increase is occurring at the same rate each second, therefore it's a constant acceleration, right? There is a term for acceleration when it changes more rapidly than this. That term I think is called jerk. We don't teach it at this level, so you don't need to worry about it. The key thing here though is that when your velocity time graph is flat, that means that the object is maintaining a velocity, right, of wherever that flat line is located. You can see the flat line there is located at the velocity of 3 meters per second. So an object that's at that point on the graph is going to be traveling 3 meters every second. Classic mistake to think that it's stopped, right? So always check that y-axis and do the common sense test of sounding it out in your mind, right? The other thing to note is that when your graph is slope is pointing down towards the origin, what it essentially means is that your velocity is decreasing over time. You are decelerating. And another interesting fact, which is a byproduct of maths, right, is that the area under the curve equals the distance traveled. For you maths nerds, the reason why that is because velocity is equal to the distance divided by time, right? But then you're timesing it by time, right? So you end up cancelling out the times, you're just left with the distance. It's quite a neat little trick there. So for any of you trying to figure out how far someone has travelled, what you can do is just figure out the area under the curve. Okay, next part of the topic is on force, mass, and weight. Mass is measured in kilograms and just means how much stuff there is. Weight is different. Weight is a force, right? Please try not to get those two confused. It is pretty easy straight off the bat to get those two confused, but that's okay if you do. You just need to be able to make sure that you understand those differences. And we measure forces in newtons after Isaac Newton, right? Big symbol N. The net force is the sum of all the forces acting on an object. Sum means to add up. So if you have 100 newtons coming from the left, 50 newtons coming from the right, 25 newtons from the top, 25 newtons from the bottom, those top and bottom newtons, they cancel out, right? Equal forces in opposite directions, right? It's not going to move, right? And you can think about like a classic classroom example of someone standing up and two mates pushing them from either side. They don't move, right? Because equal forces coming from those other sides. However, on the left and right, you can see you've got 100 newtons coming from the left and 50 newtons coming from the right. Less force on the right, more force on the left. That's going to push our object over. The net force is the difference between the two, which is 50 newtons, right? 50 newtons traveling to the right. The other thing to keep an eye out for here is the direction of the arrows. Sometimes they will be pointing out, sometimes they'll be pointing in. Just take a note of that. We sometimes write a little subscript net to let us know that the particular force we're talking about is the net force. You might see that used. If net force is 0, then all the forces are balanced, right? And that brings us to our second formula, right? F equals m times a. M is our mass, measured in kilograms, and a in this case is our acceleration, lowercase a. This is our FAM formula. So we can figure out, because we know the force on this box, it's 50 newtons, and we know the mass of the box, it's 10 kilograms, so therefore we can figure out how much this net force is going to accelerate our box. And all we need to do there is plug the numbers into our formula. So we've got 50 newtons equals 10 kilograms times some unknown acceleration. We can get rid of the mass or move it to the other side by dividing both sides by 10. So we end up with our acceleration is equal to 50 divided by 10. That means our box is going to accelerate at 5 meters per second squared, right, over to the right. So it's going to increase its speed from whatever it was starting. If the net force is 0, right, there's no force, mass is the same, therefore acceleration is 0, right? Because in order to get it equaling a force of 0, you need to times it by 0. So if the net force is 0, there's no acceleration, no change in velocity. Okay, and that relates to the 3 Newton's laws, which you should know, which is law 1, a body at rest will remain at rest. So basically things stay where they are, or they keep moving how they're moving. And that's quite a counterintuitive one here on Earth, but if you go up to space and you throw something, it will keep moving forever. If any of you have seen the movie Gravity, you'll see the George Clooney flying off into space, and he just keeps going in the exact same direction the whole time. Spoiler alert, sorry about that. Law 2. The force acting on an object is equal to the mass of that object times its acceleration. We just did that. That's FAM, right? That's our force equals mass times acceleration. That's all law 2 is. And law 3 is for every action there's an equal and opposite reaction. So if I push on a box with 50 newtons, it's going to push me back with 50 newtons, right? You can think about yourself in space. If you were to impart a force, you would essentially both be imparting a force on each other, and you both accelerate. And the amount that you would accelerate will be relative to your difference in masses. Last thing to remember, acceleration is the change in velocity over time, right? It's really easy to talk about how things increase in speed. I just avoid it, right? Because you end up in some messy territory, right? Talk about it in terms of how it changes its speed, right, over time. Yeah, that's something to keep in mind. All right, pressure. Now here's where things get a little bit tricky, right? Pressure equals force divided by surface area. Area uses a big A, right? We measure our force in newtons, and we measure our pressure in these units called pascals. surface area is actually measured in meters squared, and you can use the formula to figure this out, but it kind of makes common sense anyway. If you wanted to decrease the pressure, you'd either decrease the force of an object or you increase the surface area, right? More surface area means you're spreading the force over a wider area. It reduces the pressure. The classic example of this is you get a balloon, and if you touch it to a nail, it pops. But if you touch it to 50 nails, it doesn't pop, and that's because you've greatly increased the surface area. Here, the force is being provided by a mass, which you can see up the top there, under gravity, right? And this kind of relates to our two-step calculations, which you might be given in an NCEA context. You'll be given, say, like the mass of the object that's there on top of the board, and then you'll be told that you're on Earth, right? Where Earth has an acceleration due to gravity of 10. In reality, it's slightly less, but 10 at this level, meters per second is perfectly fine, right? You would then times the acceleration due to gravity by the mass, and that would give you the force, right? And then you would divide that by the surface area to figure out the pressure. So there will be some sort of stepwise calculations. If any of that is something you need to work on, then I suggest practicing that. Okay, the third and final part of mechanics is energy and power. Now, there really are only 4 formulas you need to know, and only 3 of them are directly about energy, right? So as long as you understand the difference between these types of energy, you should be golden. The first type of energy you need to know about is gravitational potential energy. So gravitational potential, or E, meaning energy, we use P at this level. In reality, there's different forms of potential energy. So you might see this given a different name in different contexts, but at this level, it's the only type of potential we really talk about. The way that potential energy is created or is calculated is using mass times acceleration due to gravity times the change in height. And we say change in height here because, if it's about the difference that is relating to the new energy that the object has. So that's our basic one for calculating the gravitational potential energy, the amount of energy that you give to an object by lifting it up higher. Kinetic energy is the energy due to movement, and that has an E symbol with a little K to let us know that it's different to our potential energy. And this formula is a little bit different. It's half of the mass times by velocity squared. Why that is a little bit interesting. It's a bit of a mathematical quirk, but the key thing to note there is that it's velocity squared, right? You double the mass, you double the kinetic energy. You double the speed, you quadruple the kinetic energy. You times the velocity by 3, you increase the kinetic energy by 9. This is why guns have so much energy, right? You got a little thing, but a lot of velocity going on. So that's kind of a thing to think about with regards to kinetic energy. The third and final form of this is work. And work is kind of what we think about when you're moving something from one place to another. You're imparting a force over a distance, right? Over some long distance. And the more distance you move an object, the further a distance you're applying this force, the more energy you're going to be using, right? So that's why we use this. We measure energy in joules using a little lowercase j. And we assume in our calculations that energy is always conserved, right? Unless we're told otherwise. At this level, it's actually really hard to understand just how much energy will be lost under different circumstances. In reality, some energy is always lost due to friction. And that will be the sort of thing you write about after you've done some calculations. Essentially, what you'll be doing for these types of questions is they'll give you something like a mass and then ask you to figure out how fast it was going. They might also give you, say, the height something was dropped from. And so you might need to calculate some gravitational potential, convert it to kinetic, and then do the steps to then figure out velocity. You could equally be given a distance and a force, and then be asked to figure out gravitational potential energy, right? So you're going to be stepping through those steps where you create an energy, convert it, and then turn it into something else. So that's something to practice. The final calculation you'll be asked to do is related to power. So power is energy use over time, right? Work over time is the classic calculation of it, but really it's energy over time. And we measure that in watts. So it's about how much energy you're using and how long it takes you. If you use lots of energy really quickly, you're really powerful. If you use some energy but it takes you a really long time, less powerful, right? So those conversion problems are kind of where the trickiness comes with energy, and it's just about practice. So I'd recommend spending some time going through those again and again and again. Okay, that brings us to the end of going through all that you need to know for mechanics. Now, obviously that's not exhaustive, so I'd recommend that you spend some time going over the parts that you think from this review you would find most challenging. So, moving on to genetics now. So I will open this one up. There are a whole bunch of different things here you need to know, and I will try and go through them all. As we're going through this, make a note of any bits that you're like, I need to review that one again, and that would be what you should spend more time on. Okay, let's dive into it. So, first things first, the structure of DNA. So at this level, you might be asked to do a little diagram of DNA. The things you would need to include in your diagram are the parts of the backbone, and that is your phosphate group, right? Followed by the nucleotide, right? And the nucleotide is connected to a base. It's connected to a deoxyribose sugar, which is connected to your phosphates. So you've got the rings here are your deoxyribose. Deoxy meaning lacking one oxygen over a normal ribose sugar. And they're connected to phosphates. So you've got deoxyribose, phosphate, deoxyribose, phosphate, deoxyribose, phosphate. And this thing labeled base, right? What that's referring to is these four options. Now, you do not need to know exactly how these look chemically, but you can see that they're slightly different. All you need to call them is A, T, C, and G. And A, T, C, and G are the four different letters that make up DNA. At each particular site, they are bonded to a deoxyribose sugar, and they form this kind of coiled ladder structure. So all you would need to draw in your diagram is the A's, T's, C's, and G's, the fact that there's a deoxyribose sugar, the fact that each of those deoxyribose sugars are connected to a phosphate. So you're going one after the other after the other. The other thing you might want to know, which is just a useful thing, is that A and T are bonded together with 2 bonds, whereas G and C are bonded together with 3 bonds. That's the reason why A's only bond with T's and G's only bond with C's. You will need to know that. That is called complementary base pairing. Complementary base pairing. Now that particular sequence of A's, T's, C's, and G's determines what that section of DNA codes for. And we call a section of DNA that codes for something a gene. And we'll come to that in a second. But the gist of understanding DNA is that once you know its structure and you know that it can be read in terms of the order of A's, T's, C's, and G's, you know that there will be some mechanism where that DNA can be turned into a protein, which is a little molecular machine that can do a job. So if you need to spend some more time on this, you're welcome to pause the video and have a bit of a review. But let's move on to understanding genetic material. So we've just had a little bit of a look at our A's, T's, C's, and G's, which you can see down here, and they're all wrapped up in this double helix, which is the name for the coiled structure that DNA forms. DNA is a super long molecule. In reality, it's all kind of actually broken up into little chunks. It's not physically separated, but when your cells are reading it, they're able to tell where sections that are important start and stop. Those sections which code for proteins are called genes. Those long molecules with all the genes within them wrap up into chromosomes. And just so you remember, you have 2 pairs of each chromosome, right? And then all of those chromosomes end up in the nucleus of your cells, and every single cell has the same genetic material. So genes, as we talked about before, are sections of DNA that code for a protein. Each protein does a job. Some examples of these which you might know are hemoglobin, which carries around oxygen, keratin, which is used in things like your nails and your hair. It gives structure. There's other molecules like actin, which do a very similar thing. And you might have heard of salivary amylase, which if you ever eat something, you get, say, like a saltine cracker and you put it in your mouth and leave it for a while, it will taste sweet. And that's because amylase is kind of like a little Pac-Man. It goes along breaking down starches into the glucose molecules that make them up. So it starts off your digestion. Now you have thousands of other enzymes that do different things, thousands of other proteins that do other jobs. And all of those are coded for by your genes, right? Now, because you have two sets of chromosomes, each chromosome has like another version, one you got from your mum and one you got from your dad, and there will be two copies of each gene in your genome, in the sequence of genetic material that you have. Now that becomes important when we start to talk about genes and alleles. Those two copies of the gene, whatever gene that may be, might be the same. They might be completely identical in terms of the order of A's, T's, C's, and G's, or they might be different. If they're different, we call the different versions of the same gene alleles. At this level, all we really talk about is dominant forms and recessive forms. In reality, there's a whole bunch of different forms of the same gene, but that's okay. We'll come to that at a later year level. You have that to look forward to. But we do still need to understand dominant and recessive. Dominant alleles are always expressed. They override the recessive forms of the recessive alleles. Homozygous means you have two copies that are the same version, same allele. Heterozygous means different, right, or opposite. So you have different copies of the allele. At this level, what we're talking about in terms of homozygous, so it comes in two forms. You have homozygous dominant, meaning you have two copies of the dominant gene, and homozygous recessive, meaning you have two copies of the recessive form of the gene. How do you get these different forms? Well, you have different sequences, and these can come about from mutations. Now, mutations can happen in a number of different ways. They can happen because you're exposed to toxins, but in reality, every time cells divide, there are a few mutations. And even in your own body right now, you have cells that are slightly different to one another. This is actually how cancer happens, but we can talk about that at a later stage. But what it really is these change in sequences. One type of mutation is called a point mutation, happens at a single point along the genome. You can see here, this T has been changed to a C. So that might mean that the protein that gene codes for acts slightly differently, and that could be the thing that causes it to become a whole new allele, right? Or in this case, it already is a new allele, but the question is whether it does something different. So there we go. Now that we talked about that, we've got to remember genotype, genetic sequence, phenotype, physical characteristics, right? And genotype controls phenotype. Because it is that genotype that codes for those proteins. In reality, phenotype is also controlled by the environment, right? Whether you grow up super tall is impacted by your genes. It's also impacted by your nutrition as a child. Like whether or not you had different things happening to you over the course of your life. So we would sometimes call that your genetic potential. But yeah, as long as you kind of get the idea that genotype causes phenotype, but that phenotype is also influenced by the environment. An example of this, of a trait that is selected for, so one of these physical characteristics that might mean let's start again. So genotype controls phenotype, right? Some phenotypes can be useful to different organisms in different places. So if we look at the characteristics of blue eyes originated because they were a useful mutation to a particular population in a particular place. They were they happened by random chance somewhere in Northern Europe, and because that population that had those blue eyes, it was advantageous to them because it helped to protect from reflections on the snow and be able to see things more clearly in snowy environments. Populations where they were exposed to lots of snow, there was a selection pressure. There was a pressure which meant that our ancestors with blue eyes had a slight advantage, right? A slightly more chance of being able to reproduce and pass on their genes. Now, over time, what that meant is that after millions of years, those populations gradually developed more and more blue eyes. Now, that trait was not selected for in more temperate places, which is why some different populations around the world have different proportions of the population that have blue eyes and brown eyes. It is much more complex than that in real life, but in general, certain traits can be selected for, and this kind of introduces us to this idea of evolution, which we talk about more in Level 2 biology. So you can stick around for that if you're interested. Okay, the next thing we need to look at is meiosis and mitosis, or you might call it meiosis to help you distinguish between the two. So mitosis is the classic one, and you will need to know the steps, the outline of the steps of mitosis. And now that is a little bit of a tricky thing to do, but that's okay. But we'll just look at the key differences here. So mitosis is about cells in the body, and when they make copies of themselves, you end up with identical copies of those cells. So that's what we use for like growth and repair, that sort of thing. You start off with a diploid cell, meaning it has 2 copies of the genome, it has 2 sets of chromosomes, I should say, and it makes another cell that also has 2 sets. Meiosis is different because it's about making sex cells, which we also call gametes. You start off with a diploid cell, and then it eventually makes a whole bunch of haploid cells, haploid meaning half of what you'd normally expect. Now, those steps of mitosis you need to know. There are 6 major ones. We sometimes wrap up the last 2 together. But you have interphase, prophase, metaphase, anaphase, telophase, and cytokinesis, in that order. And each of those are kind of outlaid here. You don't need to know them in a whole bunch of detail, but you do need to know the gist, right? There are some really good rhymes online to remember the order and the sequence. You, with mitosis, start off with 2N, which just means 2 sets of chromosomes, one from your mum, one from your dad, right? And when we say diploid, what the die in that means is 2. Ploid refers to chromosomes. Sex cells, gametes, are haploid, so they have 1 set of those chromosomes. And the reason for that is because you have the one gamete that is an egg and the one gamete that is a sperm, and then they join together to form a whole new organism, which is pretty neat. So all you need to know is those steps. I know it feels like a lot, but give it a go. You also need to talk about what is the same and what is different. This is a kind of classic question to be given. So this is an example of some of the things you might say that relate to the two, right? When they're used, where they're used, how they produce the next generation, what number of cells are made, all that sort of stuff. So review this if you need to, but you should be able to have a talk about that. The next thing you need to have some practice on is Punnett squares. Now this is actually something that a lot of students enjoy doing, so they get some practice in and they find that they're actually pretty good at it, right? So you take your one parent and another parent and you look at their genes, and remember each of these boxes is a 25% chance. So you look at, what's the probability that their offspring will have blue eyes versus brown eyes, for example, right? Now remember, for this one, you need to calculate both the genotype ratios, which is those genes, and the phenotype ratio, right? But you'll notice here, if we look at the phenotype and the genotype, they are different, right? We have these heterozygotes, right, that are big B, little b in this case. Now they're always going to have brown eyes, same as our big B, right? But our actual genotype ratios and phenotype ratios will be slightly different because of this. So you need to do both. So my suggestion with this is to get in some practice, different scenarios, different parents, seeing what those outcomes are. The other thing to think about is biological sex. So sex determination and why the probability of giving birth to a child that is XX or XY is 50-50. And you can do that by plotting these chromosomes, right, into these boxes. And if you replace, say, the little b over here with an X and the big B with a Y, and do those steps, you'll notice you get 50% XY and 50% XX. And so the XY parent is the one who is determining the biological sex of the offspring, right? Whether they receive the X gamete or the Y gamete. That's the gist of it, right? The last thing we need to talk about is these pedigree charts. So pedigree charts, you might remember, are these circles and squares. So when you got circles and squares, you're thinking about the next generation down, and you can draw these kind of nice family trees. You can then look at how certain traits are passed around the family and how they're expressed, right? And you can figure out from one of these family trees whether a trait is a dominant or a recessive trait. Now, the word autosomal here just refers to any gamete that isn't a sex gamete, right? I think X-linked or Y-linked, those are a little bit complex. I don't think we touch them at this level. If you're interested, you can learn a little bit more about them though. The gist of this one though is we need to know how to read these. So remember, the parents are always on the top. If it's a horizontal line, that means they bred. The line that comes off that links to all the offspring produced by that couple. And remember that the key thing is that the ratios that you see in these aren't always going to be the same as the ratios that you would predict. And that's because of probability, because each child that is born has a random chance, or has a chance of having that trait. If the chance is 50%, there might be a situation where a family has had 4 children and none of them express that trait. That doesn't mean that the parents weren't carriers. That just might mean that that's how chance works. So that's the end of our genetics topic. Hopefully that was okay. If there were any parts in there that you needed additional help with, that is something that you can write some questions down and please bring them to your teacher. You're also welcome to review those topics through things like Education Perfect or SciPad or your notes. Okay, let's move into our last topic, get through it quick, acids and bases. So, acids and bases. We need to start off with the fundamentals. Hopefully you remember that atoms are made up of 3 things: protons, electrons, and neutrons, and that protons are positively charged, electrons are negatively charged, and neutrons have no charge. They're neutrally charged, right? Classic mistake is to flip the electrons to say they're positive. Don't be making that error, okay? The next thing we need to know is how to read the periodic table. So periodic tables have little sections that kind of look like this. You have the element symbol, which is usually received from whatever the original name for the element was. So some of them might not be the same. So for example, sodium's symbol is big N, little a, right? That used to be, sodium used to be called natrium. It isn't anymore, at least not in English-speaking countries. There are some countries where the word for sodium is still based on that original word, but the symbol remains Na. The way that we make sure that we don't get confused with this is we always start with a capital letter for an element symbol, and then we use lowercases after that. That means if you ever see a chemical formula and you see a lowercase letter, you know that it relates to the element that came before it. That's how we don't get confused between copper, carbon, and uranium, right? Cool. So, next thing you'll see is the element name. On the table that you'll be given in the exam, you will not have this. So you will be expected to know just from the element symbol, particularly those first 20 elements. In the top left corner usually, or the smaller number of the two, you'll find the atomic number. The atomic number is the number of protons, right? The way that life works is that we've decided that the number of protons determines what we call the atom. So if we find an atom in the wild and we hold it and we look at it, and we see that it has 6 protons, it is a carbon, right? That's where the naming comes from. It's not like the other way around. You can't have a 5 proton carbon. Yeah, it's not how it works. Anyway, the second thing you need to know is atomic mass. Get rid of weight. I hate that it's in there. It's wrong, right? It's atomic mass. The atomic mass is the number of protons plus the number of neutrons. And the reason for that is because the mass of each of those protons and the mass of each of those neutrons is one atomic mass unit. We just add them all up together. Cool. Now that you know that, we should be able to do the rest of this. So, now that you know the different parts, you will remember, hopefully, that protons and neutrons live in the nucleus, in the center of the atom. Electrons live in the shells, in electron shells that orbit the atom. We have 4 shells that we deal with at this level. The first shell can only hold 2, all the rest hold 8 as far as we're concerned, right? So the first shell holds 2, the next shell holds 8, the next shell holds 8 after that, and it's always more stable if the electrons are hanging around in the lowest possible shell, so we always fill from the innermost shell. So if we had something like carbon, which we talked about before, has an atomic number of 6, we start off filling in the middle. So we fill our first shell with 2, we've got 4 left over, so we have 4 electrons in our second shell. We call the outermost shell that we're using for that atom a valence shell, right? There we go. This might come up from time to time, isotopes, right? So we'll talk about ions in a moment, but isotopes are the other kind of funky form of atoms. Isotopes happen when there are different numbers of neutrons. We don't basically talk about it more than what information is on this slide. Here you can see we've got helium-4 and helium-3. Helium-4 is the most common form, that's the one in the bottom. 99.99998% of all the helium in the world is helium-4, whereas helium-3 is much less common but is quite useful in certain cases. So sometimes we want to have a different number of neutrons. The number that we stick after it is equal to the number of protons plus the number of neutrons, right? So helium-4 is slightly heavier than helium-3. Now, sorry I'm a little bit out of order here, but just something, because we're going to come to it in a second. When we're writing chemical formulae, we need to make sure that we are using our superscripts, our subscripts, and our numbers in the front. Whose name I forget. That is not called the superscript. It is called the something else, which I will find out later on. So the key thing is, you've got, why don't we skip past this one because that's incorrect. Essentially the gist of this one is that you have coefficient. That's what this should be. Coefficient. So let's change this to what it should be. Coefficient. So the coefficient is out the front. Coefficient tells us how many of that molecule there are. The subscript, meaning lower script, tells us how many of a particular atom or group of atoms there are. In this case, the subscript number is next to the set of brackets, so that's telling us that everything in the set of brackets you times by 2, right? One thing to remember about chemists is that they're lazy, so they never use the number 1, right? And that's pretty sensible, because there's a lot of 1s usually in chemistry, so you don't want to be writing all of them, so they avoid them. So technically speaking, that calcium should have a little 1 to the bottom right of it, but we don't bother with that. Same with the oxygen, same with the hydrogen, right? But we don't bother with it. So if you need to, in terms of counting atoms, have a think about this, you can imagine that little invisible 1. Superscript, right, is the number that appears right at the top. Right? Usually it has a plus or a minus after it, because in chemistry we reserve the superscripts for talking about charge. So we'll come to that when we start talking about ions. So ions are charged particles. They are they occur when you have a different number of positive protons and negative electrons, right? A polyatomic ion is an ion that contains many atoms, right? And so we've got a couple of examples down there on the bottom. NH4 has a charge overall of 1 plus, and CO3 has a charge overall of 2 minus. So we write those in the superscript up the top there, and that means that we don't get confused between the number of atoms there. So we always write the number of each atom as a subscript, the number of the charge overall as a superscript, and the coefficient is the number of that molecule that there are. The other thing to know from this page is cations and anions. We love cats, so cations are positively charged. You might remember anions sounds like onions and it makes you cry, so they're negatively charged. This becomes important when you start looking at these and you need to label the difference. So this one over here is a cation, the CO3 2 minus is an anion. In the exam you will be provided a table of ions. Your table of ions will be very helpful, but it will not have the names of those ions on there. So it'll be a little bit less useful than this one here. The gist of it is that they're organized by the charge. So it kind of helps you to think about like, oh, when calcium becomes an ion, what will its charge be? But we're going to talk about the fact that you can actually deduce a lot of these without needing to use this. You will notice though that there are a bunch of polyatomic ions in this. For example, hydrogen carbonate, nitrate, carbonate. Those ones might be quite useful to you. Ammonium, all ions which have multiple atoms in them, so they're polyatomic. We will talk to you about just now about how to deduce, say, what the charge of calcium will be. So here you can see periodic table of elements. You'll be provided one of these without the names. If you want to be able to figure out the charge that something is going to be able to make, we can use the position in the periodic table to help us to do that. One thing to note here is anything to the left of this kind of squiggly line here is a metal. Anything to the right is a non-metal. In general, anything to the left of here is a cation. Anything to the right here is an anion, except for these purple ones, which are noble gases, which can't form ions because they're already so gosh darn stable. Next thing to talk about is rows and columns, or periods and groups. Periods are horizontal, right? Period is the way I like to think about it. Each period we count down from the top, and each period refers to like a new shell of the electron. That's how that, of the atom. So that's how the periodic table was organized, right? So this comes from some slides we used a while ago where we had a little task around this, but that's okay, we don't need to do that. Next thing is groups, right? Groups are about how many electrons are in the outermost shell. This is a little bit confusing though, because we actually number our groups in relating to a little bit more of a complex way of looking at electrons. But in general, the way that I like to think about it is if you're in the first two, that's pretty straightforward, right? 1 electron in it, 2 electrons on the outermost shell. These ones all here, the way to think about them is how close are they to the last group. So if you're in G17, you're 1 away, right? You have you need 1 electron. If you're in G16, you need 2 electrons. If you're in G15, you need 3 electrons, right? Some of the ones can exist in different forms. For example, iron, which is hanging out in the middle of our periodic table. Let's see if we can find it here. Here we go, here's iron. We will tell you if it is iron with a charge of 2 plus or iron with a charge of 3 plus. But you can see that it can exist in both forms. We use Roman numerals to demonstrate that, right? So iron 3 and iron 2. I think that's pretty much the only example of this that you might come across. Okay, now we talked about that. Ionic bonds and compounds. Ionic bonds are bonds between ions. Oh my goodness, who saw that one coming? Essentially, when you have a cation and an anion, they are oppositely charged. They're so tiny that even if they're like, really, even though they're super, super small, right, because they can get so close together, when they do, they slam together and they form a bond that's quite sticky. right? Because they have these opposite charges. Sometimes water can get between them and separate those. You've been learning about that for the other internal that we've been teaching you on chemical reactions, right? But in general, those ions stick together because of their opposing charges. Now that you know how ionic bonds work, you need to know how to name them. Now, naming them is a skill, and it comes with practice. In general, there's a few rules to go by, but I recommend just doing practice with these, and Education Perfect's a good way to go for that. So start off with the cation, right, the metal, and then the anion. After that, you normally just keep the cation the same. You don't need to do all that much. The anion will have weird suffixes, depending on exactly what it is. An example of this is sodium and chlorine, right? When they become ions, you get sodium with a charge of 1 plus, chlorine with a charge of 1 minus. They slam together. The cation, which is sodium, goes first, so it's sodium. Chlorine goes after and has the suffix "ide". "Ide" is pretty much the most common suffix you'll see. You will also see the suffix "ate", A-T-E. "Ate" means it has oxygens in it somewhere. There will be some other ones which you kind of have to rote learn a little bit, and then you might see numbers in front of them. Usually the number di or tri means more than one. So di in this case means 2, tri means 3. So you stick that in front of the thing that has the duplicate. So an example of that might be magnesium chloride. Magnesium has a charge of 2 plus, whereas chlorine has a charge of 1 minus. So to make it balanced, you would have magnesium dichloride, right? So that's the gist of it. The big exception to this rule are our 3 major acids, which all have nice, unique names. So hydrochloric, sulfuric, and nitric are the 3 acids we talk about. HCl is always written with an L. The L will be lowercase because it's chlorine, right? It's not an uppercase I, so don't let that confuse you. Sulfuric acid is H2SO4, nitric acid is HNO3. All of these are acids because they give up their H. Their H is an H+, that's the cation in this case. And those H pluses go into usually water and then can react with other things. The amount of those H pluses will determine the pH, right? So more H pluses is a lower pH and a stronger acid. Now pH is a logarithmic scale, which means that a pH of 3 has 100 times as many H plus in there compared to a pH of 5, right? Just like the Richter scale for earthquakes. You probably already remember this, but if you don't, pH of 1, super acidic. pH of 14, super basic. pH of 7, neutral. Cool. We can test the pH using indicators. Indicators are compounds that change color based on the pH. Universal indicator is the most common one we deal with. You might have also dealt with litmus paper or phenolphthalein, but universal indicator is red for super low pH, and violet for super high pH, and green for neutral, right? If you need to, you can refer to this table here to help you with that. In reactions with acids and bases, and in the reactions under universal indicator, what's really happening is that your H pluses are coming in contact with OH minuses and forming water, right? We call this a neutralization reaction. When acids and bases react, that's what is occurring, and that is why an acid can neutralize a base. You also should remember that a base that is dissolved in water is called an alkali, so you might see that word come up in exams. And you need to know a couple of different properties about acids and bases just to kind of know what the difference is between the two. Acids taste sour because our tongues can detect H plus ions. They can also corrode things. I shouldn't have written dissolve, it should actually be corrode. Corrode, is that how you spell that? Yeah. And bases they taste a bit bitter and they feel slippery, like soap. That's why we use basic substances to clean things, such as sodium hydroxide. If you have a gas made in a reaction, we're talking about this because we're about to talk about reactions. If you have a gas that is made, you can test for it. The 3 tests you need to know are the lime water test. When you bubble CO2 through lime water, it turns it milky. H2, or guess the hydrogen gas. test for hydrogen gas is when you make hydrogen gas in a test tube and then light it, it should make a nice squeaky pop, which is like a little mini explosion. The last one, which you may need to know, but is our least common, is oxygen gas will relight a splint that's been previously lit. A splint is just like a stick of wood. If you imagine you got a little stick, you lit it on fire, blew it out, you had that kind of ember on the end, put it in the presence of O2 gas, and it will relight. And you know exactly why that is, because that's how fires work. There are only 4 major types of reactions you need to know, but you do need to be able to figure it out from just the reactants, right? You then need to be able to turn it into a full written equation. The full reactions are there for you, right? A base plus acid equals metal, salt plus water. I've written metal, salt there because sometimes that gets confusing, right? But it's essentially you've got the metal part and then the part that makes it a salt. Some people just call it salt. That's fine too, right? Metal plus acid equals metal, salt plus hydrogen gas. So if you drop, say, magnesium into some hydrochloric acid, you're going to get some bubbles. If you put your finger over the end and then put it next to a flame, it's going to make a squeaky pop that tells you it's hydrogen gas. If you get yourself a carbonate, say sodium carbonate, and you add it to to an acid, you're going to end up making some carbon dioxide. You're also going to have your metal, salt, and water. Basically the same reaction with the hydrogen carbonate. Hydrogen carbonates and carbonates, in our case, do basically the same thing. They make metal, salt plus water plus carbon dioxide. So really, it's only 3 reactions, and you can just kind of conclude that the same thing is going to happen for hydrogen carbonates. The only thing to do is just to make sure that everything is balanced when you're going through these. Remember, the number of atoms on each side need to be the same. And as long as within each molecule you've written it correctly, the only thing you need to do is put the right coefficients in place to ensure that the number of atoms on the same side is different. The number of atoms on both sides is the same. It's a classic example here. You have Mg, HCl, MgCl2, because magnesium has a charge of 2+, Cl has a charge of 1-, so that's how we need to write that. Hydrogen always comes as a gas as H2. So therefore, in order to make sure that we have the same number of atoms, we put a 2 in front of here. So we say we have 2 molecules of hydrochloric acid react with 1 molecule of magnesium to make this reaction occur. Cool. The last thing we need to talk about in all of our topics is particle theory, which is also related to rates of reaction. So reactions occur when particles bump into one another. They need to bump into each other, and they need to have enough energy when they bump in order to react, right? We call this particle theory. There are 4 things you can do to increase the rate of reaction, which is like how quickly a reaction happens, right? And there are all sorts of ways to measure rates of reaction, but you get the idea. The 4 things that you can do are use a catalyst. You add a catalyst in, and the reaction will occur more quickly. Classic example of this is Elephant's toothpaste, right? Adding in copper, or in some cases yeast, or whatever catalyst you want to use, that's what facilitates that reaction. Look to Mark Rober's videos for more stuff on this. The reason why this works is because catalysts lower the amount of energy that it takes to have a successful collision. Concentration. If you increase concentration, right, it's a greater chance that things are going to bump into one another. As a result, reactions happen more quickly. That kind of makes sense, right? You use a stronger acid, you're going to have a faster reaction. Reason for that is there's literally more stuff there, more stuff for things to bump into. Surface area. If we have a substance with a low surface area, there's a whole bunch of atoms in the middle that aren't exposed, right? So, for example, they're showing a solid chunk of magnesium versus magnesium powder. You can see here, you can't have a reaction occurring to those particles in the middle. That's why surface area matters. So the more surface area you have, the faster the reaction will be. You can also think about this in terms of cooking. If you cut up your vegetables before you pop them in your stir fry, they're going to cook a whole lot faster. The last one here is temperature. More thermal energy means more vibrations. Vibrations mean not only are the particles moving around more rapidly, so they're more likely to collide. When they collide, they have much more energy, so there's a greater chance that those reactions will be successful. Right? So temperature is really useful in terms of increasing the speed of reactions. Lower the temperature, you lower the rate of reaction. The last thing you might see is graphs. So graphs on rates of reactions can happen from time to time. I realize my camera's gone out. There we go. We pop that one there. Haha, there we're back. Okay, so yeah, so there we go. Don't know how long it's been there for. Sorry if that was the case. So products and reactants. So here you've got a reaction that is occurring. You have some products, they make reactants. Eventually your reactions are going to stop because you're going to run out of stuff to react, right? As you have less stuff, there's less of a chance that those reactants are going to be able to bump into each other because there's just less of them. You've got a lower concentration of them in the space. So reactions slow down over time. And that's it. That's everything. In just over an hour, we've covered everything roughly. Not super well, right? Hopefully this has given you an idea of exactly what you need to cover for these externals. My suggestions would be that you go through this and make sure you make a note of which parts you found confusing. You review those parts using EP, notes, SciPad, all of that sort of stuff. And you can ask us, ask your teachers exactly what you need. The second thing I'd recommend is doing lots of practice tests. The more practice you get in a formal testing situation, the greater chances of success you will have. You will also get an accurate understanding of whether you actually know stuff. A lot of times it's really easy to feel like you know stuff, and then you actually get to the test and you kind of have a bit of a brain blank about it. So more practice tests, particularly for the longer written questions and for those problem-solving questions. Lastly, it's really important you look after yourselves. This has been a very tough year, and you are doing your best, and I'm super proud of how well you all are doing, but please look after yourselves, okay? All right, karafiua. Have a lovely rest of your day, and if you've got any pātai, just let me know. Happy to do my best to answer. Right, ka kite.